this lecture we're going to look at the transverse shear in beams, and we want to remember that complementary property that shear has in the fact that shear acts on one face as well as on an opposite face, like we have in this little picture right here. So shear not only acts on the cross section, but it acts longitudinally along the beam as well. We're going to use that to our advantage to develop how much shear is developed in the cross section of a beam. So we're actually going to use horizontal equilibrium. So if you think about a beam that's loaded as so, we're going to actually do equilibrium longitudinally along the axis using that complementary property that we have for shear. So I'm going to pull out a tiny little dx right here. So I have a little dx here. It has a neutral axis. Okay, and what I'm essentially trying to do is find the shear at this point on the cross section, which is equivalent, due to the complementary property we just talked about, the shear on this surface right in here. Okay, so basically we're going to cut it, slice it at that, and we just get this little piece right here. So again, I've got some stresses acting on these surfaces on the cross section. Those have to be balanced by the shear stress acting on that section surface right here. Okay, so that's what we're going to develop. So essentially, when I sum the forces in the x, I've got the stress on both sides has to the stress on both sides plus the shear stress on that cut surface have to equal 0, and that's essentially what I have here. Okay, where I have sigma prime dA prime sigma dA prime, where A prime is the area above where I'm considered looking at the system, and then that's got to equal tau times the area down here, which is Tx times basically the width across where I cut it at T. So manipulating this a little bit, okay, and using our flexure formula we used previously, I can find those normal stresses relative to the moment stress by essentially my over I, and that's what I have here. So I have d plus dm on this side and just m on this side, so that's what I have here. And again, that's my over I. Okay, and that's what sigma equals times each of the dAs. Okay, well, what happens here is the m over i's cancel. I'm just left with dm over I, okay, which is going to be constant relative to my area here. It is not constant relative to the x-axis, but relative to the area over which I'm integrating, right? I'm integrating over this area, okay? That moment is constant. So I bring that outside as so. Now, solving this for my shear force, or shear stress, which again is on this flat surface that I've cut, okay, I get the following. Pulling out everything that's constant, which include the moment of inertia of the entire cross-sectional area, T, which is the width at the location that I'm looking at, okay. Then I have dm dx, okay, just with the dx over here, and I'm just left with this then integral of y dA prime, okay. So here's what I've got. Dm dx, you'll remember in our discussion, is actually v, right? The derivative of the moment is my shear force, so I put that. And then I lump all of this garbage here, this integral, and I call that the variable q. So I'm left with vq over it, where q is this integral of y dA prime, which effectively is the centroid of this area right here, times the area. Okay? So I'm looking for the centroid of the area above or below where I cut, and that's how I get Q. So it's kind of a weird equation, but again, it comes from the fact that I'm summing the forces horizontally rather than vertically on the face. Okay, so that shear stress at some location is VQ over IT, and V, I, and T we've all talked about before. Q is the new thing, which is equivalent to the centroid of the area above where I'm looking times the area above where I'm looking. Okay. Now, because of this, Q is maximum, okay, at the neutral axis, right? The biggest that this can get is at the neutral axis, because that's where half of the area is. Above the neutral axis, I should have the same area as below the neutral axis, basically, by definition. Okay, so the maximum occurs at the neutral axis, making this as big as possible. Okay, now quickly, and you can look in the book if you want, but this does not apply to very, very short flat beams or points on a cross section with abrupt changes or an incline boundary. And I will refer you to your textbook if you really are interested in that. But again, for our standard beams, T-beams, I-beams, rectangles, this is how we do it, and it follows this equation, which is VQ or IT.